Okay. So, let's see. I'm grading the exams. They're going well. It's just that before I post the grades, like kind of need to finish grading all the other classes. But yeah, um, the so far they're so good. The I'll let you like for sure you wouldn't have your grades by the end of the week or next Monday, the latest. But I need to finish also creating the other classes and then I'm teaching. Uh, and also like I cannot post them before like yeah, everyone has taken the makeup. In terms of like the what's next in the course, so the idea we have 2 more weeks before the spring break. So by then we would have finished everything that's non-integration related. So in fact, we may start a little bit about integration before the spring break starts, but like that's let's say like for sure everything that's non-integrals is before the spring break, and then yeah, so then the second exam is after the spring break. Usually like people do better on the second exam. I think it's more like mechanical, more predictable the problems, but still they're the thing about this course is like every exam does have like a different flavor to it. So, you know, the first exam, like if you think about it, there was basically no derivatives. The second exam is mostly about derivatives, and the third exam is most like which is the final, it's mostly about integrals. So every exam does like has very different skills. Um, but that's more or less where we are at. Um, and yeah, besides that, um, like this, so this week we return to normal for recitation, so like there will be the quiz and then the workshops. But that's more or less the plan for the upcoming few days. So today, what I was going to tell you about is about directional derivatives and the gradient. Gradient. First, just let me remind you what we were talking about last time, which was the partial derivatives. So the idea with the partial derivatives is that you have a function of two variables. Okay. You have a function of two variables, and this here. So one way to think about it again, which is not you don't have to in that way, but it's kind of convenient, is that if you think of the function as like the temperature at the point x comma y. Just as like an idea to keep in your heads. So you're measuring the temperature at every point on the floor. That's one way to think about it concretely. So that's like what the function is telling you. So maybe here, like the temperature is 50. So the value of the function is 50 here. And then here, like it is 45. So the value is 45. And here is 40, etc., etc. Right? So the temperature changes from point to point. And so you can ask how much is the temperature changing if you just move, like, for example, in this particular direction, right? So that would be moving, like maybe let's say that's moving parallel to the x-axis, right? And so when you move parallel to the x-axis, right, only the x variable changes, and that was the partial derivative with respect to x, right? So this is the rate of change of f with respect to x, or how much f changes as you vary the x variable, right? So this is like a derivative when only x changes. Okay, and then yeah.
Yeah, I know we were illustrating with the horizontal and vertical lines, but would it be possible to like kind of like just rate of change as it's like on the line, like let's say like y equals x, or like.
Yes, in fact, that's like what the directional derivative will be. So it is like a generalization, if you want, of like the partial derivatives when the line is different from the x or the y axis, if you want to say it that way. But yeah, that's exactly where we're headed. So, but just so finish this picture. So the idea is like, yeah, like if you think about it in this way, this is how much like the temperature is changing when you move along this line. And then you could ask, oh, how much the temperature is changing when I move along this other line, which I'm drawing to be parallel to the y-axis. So when only y changes. But yeah, like it, it's kind of like natural to say, like if you're on the plane, you can move in other ways which are not just these two directions. So you could ask, what if you're moving like along y equals x or y equals 2x, etc., etc. So there's, let me draw it this way. There is, there are other lines possible. So here we just have to think like be a little bit careful with the notation. So let me call this point x naught, y naught. You'll see why in a moment. Okay, but now I could ask, well, what, like maybe this looks like 30 degrees or 45 degrees. So like maybe you could just ask how much the temperature is changing as you move along this line, right? And that's one reason why we talked about lines earlier, right? Because we had to think about how to describe them. And so if you remember, like a way to describe a line is in terms of its direction vector, right? So let's just like draw like a vector that will serve as its direction. Okay, so this is going to be a line with direction vector. Vector v. And so yeah, we would like to have something like how much is the function changing when you move in this direction. So this is not the notation that you use, but like just to kind of try to explain where I'm headed. You kind of want to know how much the function changes in this direction. So again, this is not like the notation that's used. So not used. What's used, but it is basically this idea is kind of this notation. So we like D stands here for derivative, just so think about this as the derivative of f in the direction v, right? So this is called the directional derivative. And this is like the derivative, right? Of f along a line with direction vector v. Okay, is that making sense? Like the idea? So it's kind of like a generalization of what we had were studying last time. Where last time we were talking about like moving parallel to the x-axis or the y-axis. Now you're just thinking about let's just move in along any random line on the plane, and you just ask how much is the function changing along that line. Okay. That makes sense. Okay, so just like as a conceptual um, question, like just to think if we understand this clearly. So what is like, here's some quick examples. We already know two of these directional derivatives, because what if you take the direction to be the vector I, right? So this means how much is the function changing when you move in the direction of the vector I. But what is the vector I? Remember, I is always like 1, 0. So I is always this vector, right? So that is a partial with respect to x. It should be the partial with respect to x. It is meant to, like, coincide in that case. So this one should just give you the partial derivative with respect to x. Okay, and let me actually put this in orange just to match that color. And likewise, if I take the vector j, the directional derivative along the vector j, it is how much the function is changing when you move in the direction of the vector j, which is parallel to the y-axis. So is that okay? Is that making sense? So it really coincides with the ordinary partial derivatives that we studied last time. And so the idea is just like essentially to extend this, to make this work for other directions in the plane. So the way I'll give you like what the formula is, it's like a cute trick involving the chain rule. So what's the idea? The idea is that once let's think about this direction V in terms of I and J, right? So you can think of V. The direction vector has two entries. Okay. And the point of if you have a line, the idea of having a line is that once you know the direction and like the point on this line, any other points on the line, right? Those are essentially the parametric equations we studied before, right? So if you take any other random point on the line, which that's why I have to call this back x naught, y naught, right? So if you take any other point on the line, or any other point on the line, we have the parametric equations, right? So we have the parametric equations. I don't know if you remember those from the first exam. It's just that x is x naught plus b1t, right? And y equals y naught plus b2t. Is that okay? So again, that's like what's giving you the x and y coordinates of any point in the line in terms of the initial point, if you want to think about it that way, and the direction vector b. Okay. So what's the interesting thing that happens here is that so the idea is that when you move along the line, right? When you move along the line, x and y becomes functions of t. That's exactly the point of like the parametric equations of the line. So if you move along the line, if you move along the line, x, y are functions of t. So I don't know if you remember the diagrams from last time. The idea is that the function f, right? We have this function f. Let me write it one more time here. We have this function f, which originally depends on x and y, right? That's how you should think about this function. So we have the function depending on x and y, right? But along the line, at least along this given line, x and y depend on t. So you can do like one of these diagrams that I showed you last time about like making changes of variables. So think about this kind of like as a, in a way, like some sort of like change of variables where x and y are just described in terms of t. So the way this is defined, this is defined basically as a derivative of f with respect to t. Okay, using this diagram. So let me just write it down for you. Let's put this here. So f, I don't, well, I guess I'll. So f becomes a function of t along this line. On this line. Okay, it may be better at this point to kind of do an example so that it makes it more clear of what I mean, like, before continuing. So like all that I'm trying to say is that imagine like, here's like a silly example, but it helps. Imagine that f is like x times y, just something very basic, right? X times y, that's a function of two variables. If this point had been 1, 1, let's say, and let's say this direction vector is like, I don't know, 2, 1, or 2, 3 to make it even more clear. So what would be the equations of the parametric equations of the line? It would be x is x naught is 1. So you would get x equals 1 plus 2t, and right, because v1 is 2 and v2 is 3, so like it would give you y equals y naught, which is 1. It would get y equals 1 plus 3t. Is that making sense? So it really, x and y becomes functions of t, and so the function along the line, right, would be x times y, but x times y becomes 1 plus 2t, 1 plus 3t. Is that making sense? So I'm just saying that if you just like focus your attention on this particular line, really like the function, which originally was a function of two variables, becomes kind of like a function of one variable. Okay. It's similar to what we were doing in the path test with limits. If you remember limits, when you look the limit at a particular path, it kind of collapses to being a limit of one variable, right? Because if you take a path like y equals mx or y equals x, it just depends on x, right? So it's kind of like similar idea, where if you just look on a particular line, the function just becomes a function of t, okay? So what I'm saying is that the derivative along in the direction of the line should more or less be the derivative with respect to t. That's what makes the most sense and what agrees with the cases of I and j. So yeah, I think that's kind of helps a little bit to know where we're headed. So the directional derivative is defined as the derivative of f with respect to t. So one defines okay. Now, what is this? Like, what is the derivative of f with respect to t? And this is actually where the fun part comes in. So if you remember, like these diagrams, what I'm trying to find in this diagram is the derivative of f with respect to t. Okay. So if you remember the chain rule diagrams, the idea is like to find the total change, you can just go through the intermediate path and compute like the like the smaller changes. So for example, let me see if I can use a color I haven't put here before. So one way to go from f to t would be going from f to x and then from x to t, right? So that would give you Where's my eraser? Here we go. It would give you FDX. Right, so when you go from f to x, it's like the derivative of f with respect to x, and then the derivative of x with respect to t. Plus. And then there's another path to go to t. And so in this other path, you go from f to y. Times y dt. The derivative of y with respect to t. Is that making sense? Now the idea is that this is actually like a useful thing to do. Why? And like you'll see two reasons why it's nice thing to do. So what is what is the derivative of f with respect to x? We don't really know because that depends on what the function is, right? So unless I give you like a specific function, you cannot really find those derivatives, right? So like I cannot replace this with anything. So let me just write it like this. But we do know the derivative of x with respect to t because I did give you like the specific change of variables if you want to think about it that way. So what's the derivative of x with respect to t in this equation? Just give you. Yeah, v1. It's just v1. Good. Okay. Perfect. And the other one, what happens with this term? Okay, again, I don't know what the derivative of f with respect to y is until I have a particular function. But I do have a derivative of y with respect to t, right? Because again, I did give you like a specific formula for x and y in terms of t. So the derivative of y with respect to t is just v2, right? Is that okay? Is that making sense? Yeah.
Is the directional vector equal to unit vector in this case?
We'll take it in a moment, but for now, like in this formula, it really works regardless, without problems. But yeah, you know, for it to kind of like just depend on the line, the convention is to make it a unit vector. But up to this point, like that doesn't matter too much. But yeah, once I do a little bit more, I'll say that like our convention is to make it a unit vector. Yeah. Good, but yeah, for now it's okay to just like think that it has any size. In fact, it's not. That is kind of more like to just follow what the book does because there's people who just like let the vector have any size and never bother about those things. Okay, so far so good. So now, okay, this formula actually looks a little bit more interesting because it's like there are two ways to think about it. What this is saying is that this derivative in the direction of this vector, right, is like a kind of like a combination of the derivatives with respect to x and with respect to y, right? How, like, you know, and how much each factor contributes depends on how big v1 and v2 are. Okay, so it's kind of like it is in a sense it's kind of like an average of sorts of the partial derivatives with respect to x and y. It's just like it's an average in quotes because you know because like usually when you think of an average like the you know like you know if you think about it in probabilities like these numbers always have to be positive and they are not necessarily positive because the entries of the vectors can be negative. But besides that, if you're just really like saying like you look at the partial with respect to x and the partial with respect to y and the derivative in any other direction is kind of like a combination of the two basic ones. So what this like the first thing is this is saying is that the derivative in any direction is determined by the derivatives with respect to x and y and what the direction vector is, which kind of makes sense because it's You know, if you're moving at 45 degrees, you can sort of expect that that should be, in a sense, similar to having moved in the x direction and the y direction by similar amounts. So this is kind of being reflected in this formula. And the other thing that you can notice, like, is that this has like a funny format because it's saying, well, you're multiplying two numbers, you're multiplying two other numbers, and then you are adding them together, right? And so there, we did see an operation earlier in the course where it's like a bunch of products being added together, right? So there is a formula that, what's the name for that? Like has a bunch of products being added. Yeah, right, it's a dot product, perfect. So it is a dot product between two vectors. Okay, which vectors I'm using the colors for a specific for a strategic reason. So if you take this, if you put like, if you just write the partial derivatives as a vector, because why not? So that you have the first entry of this vector will be the partial with respect to x, the second entry of this vector will be the partial with respect to y. And then if you do that with the dot product with v1, v2, right? Then doing the dot product between these two things is exactly this thing in the middle, like this thing that we had before, right? The nice thing about writing it this way is that what is this vector in green? That's exactly the direction vector. So this one is no surprise. This is essentially what we started. So it looks nice because of that. And what is this thing? Well, I haven't told you what this is, but this is called the gradient of the function. So this is where the gradient appears, and I'll call it grade. I mean, like I'll give you some notation in a moment, but this will be called the gradient. So if in fact that is how we're going to think about this directional derivative as a dot product between the direction vector and the gradient. So let me rewrite this in a slightly better way. So this is like the formula that we have to use. Okay, so if you have a function of two variables, if f of x, y is a function of two variables, So let me say, it is a formula for the directional derivative. Then the gradient of this function, the gradient of the function, let's see which converse to use. I'll use this. Yeah, actually. The gradient of f. And I'll show you a couple of things in a moment because it is actually one of the important parts of the course. So the gradient of f of the function is a vector. Well, is the following vector. Okay, so well, I'll spend some time telling you more about this, but just to finish writing this off, the idea is that once you have the gradient, which is going to be a vector, it's a vector of partial derivatives. That's one way to think about it. Just a vector whose entries are the partial derivatives of the function. Then the directional derivative is just the dot product between the vector and the gradient. Then derivative is Uh, I'm going to spend some time first, like telling you what the gradient is, and then I'll return to the directional derivative formula. Um, and we'll use it in practice, but it is useful to like at least have some idea what this gradient thing is. And like today, we'll spend like basically all the class discussing these two formulas and what they're useful for. Okay, so let's start with some examples of what the gradient is. And then I'll return to the direction derivative formula. Let me start with something easy and then I'll just increase a little bit of it. Here's a very basic thing you could do. So you could take a function like x plus 3y. Okay, that's a function of two variables, right? And then to find the gradient, what you always do is find the partial derivative. So you can find the partial derivative with respect to x. That just gives you 1, right? And then you can find the partial derivative with respect to y. That gives you 3, right? Okay. So the partial derivatives are just those two. In this case, happens to be constant. I mean, they don't depend anymore on x and y. I'll do a more complicated example in a moment. But at this point, like they just happen to be those two things. And then the gradient is by definition just the partial derivative written like in vector notation. So the gradient. So this is like an inverted triangle called nabla. Like like kind of one of these Greek letters, but you don't have to worry too much about that. You probably have seen it like in the fraternity signs. So that is again like some useful application of fraternities. You just like understand the match symbols of multivariable. So like the grading is always just the partial derivatives written kind of like alphabetically. So partial with respect to x followed by partial with respect to y. So this is 1, 3. And yeah, you see a vector, right? So the vector 1, 3. So the way you think about the gradient, the way you're going to think about the gradient is that gives you the vector 1, 3, but something interesting happens here, which is a little bit different from what we were doing before. So if you remember at the beginning of the class, I told you, well, you should think of the vectors kind of all being drawn at the origin, right? Here we're going to do a slight modification of this, that idea. So let's just draw this vector first in the origin. So 1, 3 probably maybe it looks like this. Okay, that could be like what the vector 1, 3 looks like. And then I'll just make copies of the vector all over the plane. So just copy, paste, copy, paste, copy, paste, copy, paste, and then just make a bunch of clones of this vector. Okay, so these are all meant to be the same vector 1, 3. I'm just transporting it all over the plane. I'm actually going to show you in GeoGebra how this looks like in a second. So you would write that the gradient of f is the vector 1, 3, which is also I plus 3j. So let me just write it like that. It's more elegant, put it in terms of I and j. Okay. And so really in this case, yeah, you would call this a vector, but if more properly, you would refer to this as a vector field because at every point in space, you're kind of drawing a vector. Okay, the terminology has something, it's not a distinction that you have to worry too much about it in the meantime, but at least let me just show you first. This looks like. I always forget that this one is manual. Okay, so for example, you can go to GeoGebra, you enter something like vector fields. Okay, and so here, like, and I'll show you what happens, like what's interesting. But here, like, you're going to enter yeah, the notation is a bit weird, but this refers to the first entry. Like if you look, just compare with this expression, this refers to the first entry of the vector, and the other one refers to the second entry of the vector. So our vector is 1, 3, right? So I'll just put 1 and 3 at the entry. Okay, so it's nothing too exciting, like I don't know if I can zoom this thing. Okay, yeah, you just see a bunch of arrows, right? Like, but they're really small, but like they're just clones, like copies of, you know, of. In fact, like I think it's just because here you can, you can choose the. I mean, like you could choose the animation to rescale the vectors so if you prefer to look at the arrows a little bit bigger, but. The point here is like, you just get a bunch of arrows. In this case, like all the arrows are 1, 3, and so they're clones of 1, 3 everywhere, right? What happens is that you can do more interesting functions, right? So let's just think about what's a more interesting situation for us. So here's like a more interesting function, and it starts to show a bit of what's going on. So uh, here's another example. Let's say I put x to be the function to be okay. So the only thing that I'm doing different now with respect to the previous function is that I'm replacing x with x squared. So what are the partial derivatives now? The derivative with respect to x is 2x, right? And the derivative with respect to y is 3, right? So the gradient now for this particular function is, again, is partial with respect to x, followed by partial with respect to y. So it gives you 2x comma 3, right? Let me see something. Okay, so what's the interesting thing that happens here versus here? So in this first situation, like the entries for the gradient of this vector aren't completely constant, right? Like they're just like numbers, right? The difference now in this second case is that the entries, at least the first entry depends on x, right? So what does that mean? Like, for example, let's say you wanted to draw, like you wanted to draw this at the origin, right? So what should you draw at the origin? Well, the value of x at the origin is 0, right? So you will get 0, comma 3, right? So like at the origin, you should draw the vector. So like what's 0, 3 is just 3j. Okay. But like now, before I just make copies of the same vector all over the plane. The thing is that now that's not so like such a smart thing to do, because now the formula for the gradient depends on the values of x. So the idea is actually that you want to evaluate this at different points to obtain different vectors. Okay, so for example, let's say you have here the point 1, 1, right? So what should you put as the gradient? So now the value of x is 1, right? So if the value of x is 1, you should put here 2, 3, if that makes sense. Right, so drawing the vector 2, 3, like vertically it's still the same magnitude, like it's still the same size vertically, but horizontally is now it has some size like in the horizontal direction. So 2, 3 maybe looks like this. That making sense? So the idea is that you adjust the vector, like before, like since the vector, the gradient did not depend on x and y, you just made the clones of the same vector. But now, because the formula depends on the value of x, you do kind of take into account where you're going to draw it, and that's why you have to pay attention into what the x coordinate is. So for example, if I were to put something like, let's put something with negative values for x, like let's put like the kind of like the opposite, well, not the opposite, but the mirror image of this point. Like if you put the mirror image of this point, you put like -1, 1, right? And so what's the vector that I should draw here? Now x is -1, so you should get -2, 3, right? And so now the vector is actually pointing to the left. So this would give you the vector -2i plus 3j. Is that making sense? So is that kind of reasonable? So that's why when it comes for something like the gradient, it makes sense to draw like a vector for each point in space, because the formula is allowed in general to depend on the particular point. So if you do the same thing, if you do the same thing that we were doing before with the other vector, let me just so the second entry was still 3, right? But now I'm replacing the first entry with 2x instead of just 1, right? So if I put here 2x, now like the vectors look like this, right? And this is why it's called like a vector field. Field meaning that from at each point in space, you can get a different vector that you are drawing. Okay, so in fact, I can kind of make this smaller so that it doesn't look so crazy. What you can notice in this particular case is like like the vertical component always has the same size, and when you fix the value of x, then the vectors are all the same, right? Because like the x value is the same. But in general, like the vectors, once you have like an interesting function, like the gradient can look like you can start doing like more cool things. So just to put like another quick one here, like if you had if you have like something like x squared plus xy, or let's put xy cubed. Okay. If you have something like x squared plus xy cubed, so what's the portion with respect to x? The portion with respect to x would be what? 2x plus y cubed, right? And the partial with respect to y would be, this one doesn't give you anything, and then you just get 3x y squared. Everyone with me? So those are the two partial derivatives, and again, you assemble them into a vector, so the gradient would just be 2x plus y cubed, comma 3x y squared. Okay, so that's the first entry, followed by the second entry. So you can put some, hopefully that looks can still be done in the animation. So you put something like this, and then 3 times x times y Where? Okay, and then all this, all like, it's a lot more, well, chaotic, maybe not the right word, but harder to understand. You would need to, you would need to really evaluate this at very different points to kind of start getting like an idea of how it's supposed to look like, which is one of the advantages of like just being able to do it on the computer, right? But let's see if I can draw it, less chaotic. But like, my point is that, the gradient produces a vector, but that vector is allowed to depend on the values of x and y. So that's why when you represent it visually, you end up drawing all these vectors of different sizes or different vectors according to the formula provided by the gradient. Is that making sense? I still haven't told you what the gradient is. I just telling you how to draw the gradient. I still have to tell you what that is, but that still requires a little bit more of like extra things that we have to do. But at least this is like the first step in the formula for the directional derivative, because the directional derivative was a dot product. Okay. So now, this was just like a bit of an aside to discuss what the gradient is. So in general, let me just write that. So the point is that this vector depends on x and y in general. This depends on in general the vector depends on x and y. So you draw, in general, you draw a different vector at each point of space. Okay. In fact, like what we'll do at the end of the course, like the gradient will kind of be with us until the end of the course, basically. But what we'll do later, towards the end of the course, is that if you think of F as some sort of like potential energy, then the gradient gives you a force because this is a vector. So the gradient of a potential energy is like a force, and those are what I call conservative forces or conservative vector fields. So essentially that's, like if you have seen like kind of like the gravitational potential energy or like electrostatic potential energy, voltage or potential energy, that those are kind of like these functions F, and the gradient that gives you the force of those things. Okay, so but again, that's actually for like something we'll do in the final. And so we have the gradient, and again, just to go back to the formula for the directional derivative, the formula is the formula for the directional derivative is just a dot product between the gradient and the direction vector. But now, hopefully this makes more sense because now we have talked a little bit more about what the gradient is. So you're just taking the dot product between two vectors. Now, back to what you were asking me, because you're supposed to think about, so far I haven't told you I haven't given you any conditions on the vector. You're thinking of the vector as representing the direction of a line, right? So if you think about it, like, let me draw the line. If you have a line, then you have this vector that gives you the direction of the line. Let me draw it here. But it's similar to the normal vector of a plane in the sense that once you have one, like you can always rescale them, and that also gives you a direction. So if someone says that this is the direction of the line, you can multiply this vector by 2, and that also is like the direction of the line. You know, so like, there are actually many vectors that work as directions of a line. So the convention for this formula, whenever we apply this formula, the convention is to have chosen a vector of length 1. Okay, so I'll choose a vector for this formula. Let me put it as convention. You choose a unit vector. So you choose the direction of the line as being a unit vector. So the length of the vector is 1. Uh, the magnitude or the length is 1. So let me give you an example of how this works. So let's try to get to, okay, we still have like almost 30 minutes. We're good. So here's an example. Let's say the function is, just to do something simple, x times y, that could be our function, and like I want to move in a line. I want to move along a line that's I want to move along a line with direction vector 1, 1. So that is, if you think about it, because both entries are the same, that is really like a line at 45 degrees angle with respect to the x-axis, or also the y-axis. So that would be, you know, that is kind of like in between having moved parallel to the x-axis or having moved parallel to the y-axis. Okay, so the question would just be like to find the directional derivative of f on b. That's fine. So it's essentially what we were doing, like you find first the gradient. So what to find the gradient again, find the partial derivatives. So what are the partial derivatives in this case? The partial derivatives are the derivative with respect to x is y, and the derivative with respect to y is x. Okay, so the gradient of the function is y comma x in this particular case. Okay, and so the answer is that this should be a dot product between this vector and the vector that I just gave you here. The only thing that you have to be careful about is that the vector that I gave you doesn't have length 1, and that's the only thing that you have to worry about. So notice that what's the length of B? Well, it's like Pythagoras theorem, right? It's 1 squared plus 1 squared. That's just root of 2. So if we don't work, we're not going to work with V, we're going to work with like the rescaled version of V. So just to follow this convention, so we use. Right, so if you have a vector of a certain length and you divide that vector by its length, then you get something with length one almost like by default. So if the vector has length three and you divide it into three pieces, each piece has length one. That kind of makes sense, right? So basically that just means dividing each entry of the vector by the magnitude or by the length. So you get 1/√2, 1/√2, and so the directional derivative is the dot product of the gradient with this vector, so you get the dot product between y-axis and okay, and that's like an easy dot product to make, right? So it's just you get y/√2 plus x/√2. So, like if you had forgotten to work with the unit vector, the only difference would have been like a factor, like it would have differed from what I just did by √2. But like, again, like the convention is to always choose it to be a unit length because one more time, like, the lines have like um, multiple directions. So I mean, if you have a direction vector for a line, any rescaling of that works as well. So like you have to make a choice at some point, and that's how it's chosen to be. Is that making sense? Okay, so let me tell you why the grade. Okay, so why is all of this important? Um, or why is the gradient important? Well, one reason is because it just happens to appear, right? It just happens to appear in the formula for the directional derivative. So that's one reason why the gradient matters. And there's another more important reason, which is the following. So now this gets us to what's the meaning of the gradient. So what I have been telling you is that if maybe you are at a particular point, you want to move in the direction of a vector given in the direction of the vector v, right? And the directional derivative of the function in that direction, because of what we were discussing, is just the dot product between the gradient and the vector. So as I was saying before, the gradient is supposed to be a vector at every point. So let's try to draw a vector representing the gradient. Okay, so the directional derivative is the dot product between these two vectors. Which is what we were doing up to now, right? Now, here's the thing. So we know how to find the dot product of vectors. We have done it multiple times, but there was, in terms of the entries, there was this alternative definition of the dot product, right? Which is the product of the magnitudes of the vectors times the cosine of the angle. So let's just think about what that is. So there's like an angle here between the two vectors. So if you use the other version of the dot product is the magnitude of the gradient, right? Times the magnitude of the vector v times the cosine of the angle between them. Okay, is that making sense? But this is another reason why I mentioned that our convention is to work with that direction that have length one, because then in this formula, if you choose if you're using directions of length one, then this is really just one, like this second factor gives you one. So the directional derivative is just the gradient of f times the cosine of the angle, right? Because again, the length of the second factor was one. Um, is that okay? So that's good. And why is that useful? Because actually this, well, it's not quite a Swiss theorem, but it has like a similar flavor because we don't know, like the direction, like this angle really depends a lot on what the direction, what this data depends on how you choose like the direction vector, right? But what we can say for sure is that the cosine is between -1 and 1 all the time, right? So this quantity, whatever this is, right? Let me put it this way. So whatever this is, because cosine is between -1 and 1, we kind of know how the max this direction, like how large this directional derivative can ever be. So the maximum this directional derivative can ever become is precisely when the cosine happens to be 1, right? That's what would make this product the largest. So this is a max, this gives you the max value when the cosine equals 1, right? What does it mean for the cosine to be 1? It means that the direction was, I mean, if the cosine is 1, that means that theta equals 0, right? So, so in terms of a picture, what I'm saying is that the maximum the directional derivative can ever be is when the direction and the gradient are parallel, right? So you have the gradient, and then you have the direction v. And so that's when the angle is 0. So this thing is largest, so the max value occurs, so the maximum value of the directional derivative occurs when the direction is parallel to the gradient. Yeah,
So by max value of the directional derivative, does that mean that if we move in that direction, then we get the greatest increase now?
correct. So perfect. So that's exactly what I mean. So right. So actually it's easier to show it on GeoGebra. But what I'm trying to say is that, like, yeah, imagine that the function gives you the temperature on the floor, right? You want to move towards the hottest point on the floor, right? So you're here, maybe this is not the hottest point, maybe the hottest point is there, right? But then you want to say, well, how can I reach the hottest point? And then the idea is like moving the direction of the gradient. The gradient will guide you towards the maximum rate of increase of the function. So that's a maximum, that's a maximum rate of change of the temperature. So that would be moving you towards the hottest point, if that makes sense.
At this point, like the absolute maximum.
Well, it would like kind of like a local max, right? Like, so if you think about it, like, if you think about it as bunch of, okay, like this is another analogy. You think about it, you have a bunch of mountains, right? So maybe you like mountain climbing, right? So the gradient, like, if you are here, like if you're not towards here, then the gradient will point towards this peak, right? If you think of the function as the height above sea level, right? So it is, in this case, which would happen to kind of agree with the absolute max of the function. But if you happen to be here, right, then the gradient would point towards this peak. So like it's really points to the local max, um, you know, of the function, because kind of like the gradient cannot see like everything that's happening all around it. You can only see kind of like around you. It's always telling you, okay, you're at this point, you want to move, you have all these directions that you can move along, right? Which is the one that will record the greatest increase in your temperature, like the one given by the gradient, or like the greatest increase in height, the one given by the gradient. It's just that like if you're here, that would actually take you to this max, but if you're here, that would actually take you to this other max, right? So it really depends on where you stand on the floor or the mountain system, but it is at least some sort of max, if that makes sense. No, but that's good. So the gradient is a vector you must follow if you want to reach some sort of max. Like, again, may not be the absolute max, but it's a max. And we'll talk about maxes and means like actually next time, and you'll see that the gradient plays a role in there. Because the point is that once you reach one of these max, you don't know anywhere else to move, right? You don't have anywhere else to move, so the gradient should stop and die, and that means that it vanishes. So like a critical point is where, or a max occurs, where the gradient gives you the zero vector. That's the basic idea, right? Okay, and then like I'm almost, I'll try to just finish this idea. And then you could ask when is the most, like it kind of sounds weird, but when is the gradient, this rate of change, the most negative? Which it would be the minimum value, right? Is that you have to think about it like the greatest decrease. So let's see. Let me put mean value here, but by that I just mean most negative. Well, is everything is reversed, so like the cosine should be -1, right? So that means that the gradient should be anti-parallel, right? Like the angle should be pi, 180 in this case. So that means that theta should be right? So like now again, imagine like you're trying to find like the coldest, not maybe the coldest, but one of the coldest points on the room, right? Like it's maybe like a local mean, or like one of the bottoms, like in this like mountain system. Then you should like kind of move in the opposite direction, which makes a lot of sense if you think about it, right? Like if you just reverse your direction, that should be, if before it was going towards like one of the highest points or like one of the hottest points, like if you like just move it the exact opposite way, that should decrease the most rapidly. Does that make sense? Okay, so I'm almost done. So the max value is when theta equals 0. The mean value is when theta equals 180 degrees, right? So cosine, that's when cosine equals 1 and cosine equals -1 respectively. But there's another nice value for cosine, right? Cosine is 1, -1. Also 0 is an important value, right? So let's think about what happens when is the directional derivative 0. So again, like for this to be 0, like what you need to make is the cosine to be 0, right? Whenever cosine of theta equals 0. Or the theta equals pi over 2. or the gradient is perpendicular to the direction, okay? Oh, sorry, I'm changing the meaning here. So what's happening here is that if you choose the direction to be perpendicular to the gradient, right? Kind of like the function, like, the value of the function freezes, like if you just move in the direction perpendicular to the gradient, there's no rate of change there. So here's like an application of that idea, and that's what I'll finish with today, and I'll remind all of this on Wednesday. So imagine again, you're mountain climbing, whatever, and then you're kind of like just tired, like so you just want to walk, but without increasing or decreasing your height, right? Like just to have like more like enjoy the view. So how you should move? You should move perpendicular to the gradient. So if you move perpendicular to the gradient, your height will never change. Okay. And what's the analog of that? What means is that if you move perpendicular to the gradient, you're kind of like making the function remain at a fixed value, right? So that's essentially a level curve. So what I'll tell you next time is one of the most important ideas about the. I'll show you this like next time again, because this is like really one of the most important ideas of the course, is that if you have a function, okay. Let's see. So yeah, let me. Oh, like maybe like you're trying to get to the top, but you got tired. So you just want to move along this level curve, right? The yellow trail, because your height is frozen there. So if you look at this, the level curve looks kind of like an ellipse here, right? This yellow curve, I don't know if it's too easy to see the yellow because of the animation, but the idea is that the gradient, which is this black vector, will remain perpendicular to the curve. So the important thing about the gradient is that as you move along a level curve, oops, let me see if I can, okay. So as you move the gradient along a level curve, which is what I'm trying to do here, I'm trying to move along this ellipse, like the angle between the curve and the gradient remains 90 degrees. Okay. I'll write this next time, so you don't have to worry about it now. And that is, I will do an analog of that next time to find like tangent planes to surfaces. But I'll explain you how that works next time. So I'll repeat some of these ideas on Wednesday, but that's more or less where we're at. Okay. So yeah, let's finish here if that's not it.